Right now, as you're watching this, artificial intelligence has just uncovered something buried inside California's most famous fault. No human researcher ever caught it, not once in over a decade of data. Scientists studying the San Andreas Fault near Parkfield used AI to sift through years of ultra-sensitive strain data and found 92 separate slow slip events. These are moments where the fault physically moves. It releases real stress without producing any shaking anyone could feel. And it does this without triggering a single detectable earthquake. Of those 92 events, 21 had never been identified before. They were hidden in plain sight inside data scientists had already manually reviewed. This is the first time researchers have built a complete picture of just how often the San Andreas moves silently. And what they found is genuinely reshaping how this fault is understood. Today, we're going to break down exactly what a slow slip event is. We'll cover how AI found what years of human review missed, and we'll get into why this discovery matters for one of the most dangerous fault systems in the United States. If you want to stay ahead of breaking science like this, subscribe and turn on notifications. We cover it constantly. Let's get into it. Let's start with what a slow slip event actually is. It's a genuinely strange concept if you've only ever thought about faults in terms of earthquakes. Most people picture a fault as something that stays locked, completely still, building up stress for years or decades. Then it finally snaps and releases all of that stress at once as an earthquake. That picture is true, but it's incomplete. Faults don't only move during earthquakes. Sometimes they slip silently, creeping forward over hours or even days. They release a portion of that built-up stress without any sudden violent rupture, and they do it without producing shaking strong enough for a person to feel. These are called slow slip events. Until recently, scientists believed they were relatively rare and difficult to detect. This new research changes that understanding significantly. A team from the GFZ Helmholtz Center for Geosciences, EarthScope, and Stanford University worked with 4 borehole strain meters. Those instruments were installed along the Parkfield segment of the San Andreas Fault. They're sensitive enough to detect microscopic deformation in the rock itself. That data was collected between 2009 and 2016. For years, researchers manually combed through that data set looking for signs of slow slip. They found a certain number of events using that traditional approach, but manual review has limits. A human researcher, however experienced, can miss subtle signals buried in years of continuous data. This is especially true when those signals are short in duration. And when they don't produce any of the obvious signatures a larger, more dramatic event would leave behind, that's exactly where the AI came in. Researchers trained a machine learning model specifically to recognize the subtle signature of slow slip events within the strain meter data. Then they let it comb through the entire multi-year data set far more exhaustively than any human team realistically could. The result was a total of 92 identified slow slip events. That more than doubled what had previously been cataloged through manual analysis alone. Of those, 21 events had been completely missed by every prior review of the exact same data. 14 of the newly discovered events were independently confirmed using nearby creep meters. Those are separate instruments that measure surface fault creep directly. This gives researchers real confidence that these AI-detected signals represent genuine physical movement of the fault. They're not statistical noise or an artifact of the detection method itself. Here's why this matters, beyond simply being an impressive piece of technical work. Stanford geophysicist Gregory Barroza, one of the researchers behind the study, has been direct about what this larger, more complete catalog reveals. These slow slip events aren't just background noise the fault produces independently of everything else happening along it. The research found that slow slip modulates low-frequency seismicity on the Parkfield segment. That means these silent, undetected movements appear to directly influence smaller, related seismic activity nearby. In other words, the San Andreas isn't simply locked and waiting or violently rupturing. It's quietly, continuously redistributing stress along sections of itself. Scientists are only now able to see that clearly, and that redistribution appears to be genuinely connected to the fault's broader behavior. This is a meaningful shift in how the San Andreas Fault is understood. Previously, when scientists modeled how stress builds and releases along this fault, they were working from an incomplete picture. They were missing close to a quarter of the fault's actual silent movement. That's simply because those events fell below the threshold of what manual review could reliably catch. With a genuinely complete catalog of slow slip activity at Parkfield now available, researchers have a meaningfully more accurate foundation. It helps them understand how stress is actually moving through this section of the fault over time, not just how it's building toward the next major rupture. It's important to be precise about what this discovery does and doesn't mean. It would be easy to overstate it. This research does not predict an earthquake. The U.S. Geological Survey's own position on earthquake prediction remains unchanged. Neither the USGS nor any other scientific body has ever successfully predicted a major earthquake. And researchers do not expect that capability to exist any time in the foreseeable future. What this study does is something different, and in some ways more foundational. It gives scientists a dramatically clearer picture of one specific piece of the puzzle. That's how often and how significantly this fault moves without producing a felt earthquake at all, and how that quiet movement relates to the smaller seismic events happening around it. This discovery also arrives at a moment when the San Andreas Fault is already the subject of intense scientific attention for entirely separate reasons. It's worth understanding how these different pieces of research connect. A study published earlier this year found that Southern California's fault system is now under more stress than at any point in the past 1,000 years. That specifically means the southern San Andreas and San Jacinto faults. That same research identified a specific structural point called Cajun Pass. That's where the San Andreas and San Jacinto faults physically meet. Researchers are calling it an earthquake gate. It's a junction capable of either blocking a rupture from spreading between the two fault systems, or, under certain conditions, allowing it to pass through and turn a single fault earthquake into a much larger connected event involving both. Separately, researchers drilling off the coast of Oregon uncovered sediment evidence. It suggests that a major earthquake along the Cascadia subduction zone could potentially trigger a second, separate earthquake on the San Andreas Fault. Cascadia is the fault system capable of producing a magnitude 9 megaquake off the Pacific Northwest coast. That evidence came from paired sediment layers formed by underwater landslides. These are patterns that suggest both fault systems may have ruptured close together in time on more than one occasion throughout the geological past. Researchers are careful to note this remains an area of active investigation rather than settled fact, but it raises the possibility of a coast-wide earthquake sequence. That sequence could impact nearly the entire west coast within a matter of hours. It's a scenario considerably more complex than a single fault rupturing in isolation. And in a completely different part of the state, scientists have identified an entirely new fault. It's dubbed the Salton Trough Fault. It runs parallel to the southern San Andreas near the Salton Sea. Researchers behind that discovery noted that the southern San Andreas hasn't experienced a major rupture in roughly 300 years. That's an unusually long, quiet stretch that has puzzled the earth science community for some time. This newly identified fault appears to be absorbing some of the strain that would otherwise be building directly on the San Andreas itself. Though without a historical earthquake record specific to this new fault, researchers say it remains genuinely difficult to determine exactly how it interacts with the San Andreas. That's true both at depth and over time. Taken together, these separate pieces of research paint a picture of a fault system. That includes the AI-discovered slow slip catalog at Parkfield, the record stress levels and earthquake gate at Cajun Pass, the potential Cascadia-San Andreas connection, and the newly discovered Salton Trough Fault. This fault system is being understood with far more precision and far more complexity than at any previous point in the history of earthquake science. Each of these discoveries individually might sound like a narrow technical finding. Together, they represent a genuinely significant expansion in scientists' ability to see what the San Andreas Fault is actually doing. That's true both during the dramatic moments that make headlines and during the long, quiet stretches in between. Those quiet stretches were, until very recently, effectively invisible. It's worth explaining why AI specifically was the tool that unlocked this particular discovery. It says something important about where earthquake science is heading more broadly. Slow slip events at Parkfield produce extremely subtle short-duration signals within continuous strain data collected over years. A human researcher reviewing that data has to make judgment calls. They have to decide which small fluctuations represent genuine fault movement versus instrument noise, environmental interference, or other confounding factors. And that judgment inevitably has limits, especially across a data set spanning 7 continuous years. A properly trained machine learning model doesn't get fatigued. It doesn't lose focus, reviewing the 10,000th hour of data the same way a person might. And it can be trained to recognize a signal pattern with a level of consistency that's genuinely difficult for manual review to match at scale. This is part of a broader trend across seismology right now. AI and machine learning tools are increasingly being applied to reanalyze existing historical datasets. Sometimes they uncover meaningful new findings, hiding inside data that had already been collected and reviewed years or even decades earlier. For anyone living near the San Andreas Fault, it's worth being clear about what this specific discovery does and doesn't change. This study does not indicate an earthquake is more likely to strike soon. It should not be read as a new warning sign in that sense. What it does represent is a genuine advancement in the underlying science. It's a more complete, more accurate picture of how this fault actually behaves. Over time, that feeds into better hazard models, better stress calculations, and ultimately a more refined understanding of how earthquake risk is distributed along different segments of the fault. That kind of foundational scientific progress matters enormously. It matters even when it doesn't translate into any immediate, actionable change in day-to-day preparedness. That said, The baseline earthquake preparedness guidance for anyone living near the San Andreas Fault remains exactly what it's always been. This research is a useful reminder to make sure you've actually acted on it, rather than simply intending to. Have several days of emergency supplies ready and accessible. That means water, food, medications, and a flashlight. Know where your home's gas shutoff valve is located. Secure heavy furniture and anything that could fall during shaking. Have a family communication plan for a scenario where mobile networks become overloaded. That happens routinely in the immediate aftermath of any significant earthquake. And if you're in California, make sure Shake Alert notifications are enabled on your phone. That system can provide critical seconds of warning before shaking arrives. It's genuinely enough time to drop, cover, and protect yourself. So here's the honest final picture. Scientists just used AI to uncover 92 slow slip events along the San Andreas Fault. 21 of those had never been detected before, despite years of prior manual review of the exact same data. That discovery reveals the fault is moving silently far more often than previously understood, and it shows that this silent movement appears to directly influence nearby seismic activity. Researchers are only now able to properly study that connection. It's not a prediction. It's not a warning that something is imminent. It's something arguably more valuable from a scientific standpoint. It's a genuinely new, more complete window into how one of the most closely watched fault systems in the world actually behaves. That window was hidden in data that had been sitting there, unexamined at this level of detail, for years. We'll keep tracking this research as it develops. That includes any new findings out of Cajun Pass, the Cascadia Connection, and the rest of California's fault systems. Subscribe so you don't miss any of it. Drop a comment and tell me if you live anywhere near the San Andreas Fault. Or tell me if this kind of AI-driven scientific discovery surprised you as much as it surprised me. I read every one of these. Stay curious, stay prepared, and I'll see you in the next one.